Wait for a minute. I want to take water. Okay, I'm back.
Okay, Prof. Ray, it is already 8, so you can start your lecture.
Okay.
Okay, please, this is yours.
Thank you. Good morning, everyone. Welcome to our course. Today, we will continue the unfinished job from the first day. I will quickly go through the 5G standard, then show you what are the major difference. I guess Professor Nana already mentioned some of the key idea, but I will want to explore more to the network part. Then today's main focus is functional split and open Fronthaul. From tomorrow, we will introduce OCU, ODU. Then on Thursday, we will discuss more about near real-time RIC. I think both topics are included in your final presentation. So if you have any question, please feel free to discuss. So let's start our discussion today. Today's talk, the contributor are our two TA, Nick Huang and Jonathan. So today I will briefly summarize the 5G standard and the network architecture for 5G standard. From 2G, we start from circuit switch, it's telephone-based service. To the 3G, we start to provide packet switch data service. It's basically IP-based service. To 4G, so in 3G, actually there are two networks exist in parallel. To the 4G, they try to merge it to a single one. They try to use voice over LTE to provide voice service over IP network. To the 5th generation, we mentioned there are 3 main service, eMBB, UILC, and massive MTC. So from LTE to 5G advanced, actually they are different release. Different release means different version of the network standard. LTE is for release 8 to 9. Actually, in this stage, they did not use OFDM. Until LTE advanced, they start to use OFDM technology. It's release 10 to 12. Now they move to LTE Advanced Pro, try to further enhance the data rate. For 5G, the first release is release 15. So 15 to 17 is almost done. Now they will move to 18. 18 will focus on 5G Advanced. So it's currently is around the end of release 17. First of all, we want to show you 2 terms, FR1 and FR2. In 3GPP release 15, they define 2 spectrum. First, FR means frequency range. So FR1 means 450 megahertz to 70.1 gigahertz. So this is normally known as sub-6 or sub-7 gigahertz band. The second one is the FR2. FR2 is about 24 gigahertz to 52.6 gigahertz. In this frequency band, they can offer much more bandwidth. So this is also refers to millimeter wave band. In 5G, they define different bandwidth. They can have up to 100 megahertz bandwidth in sub-7 gigahertz band. For millimeter wave band, FR2, they can have up to 400 megahertz. So you can know the bandwidth come from the requirement for eMBB. What's the impact for the band frequency? As we mentioned, for high frequency, in the first day, we show you the propagation model. Professor Trier also show you the channel model. The major challenge for higher frequency is they will have a higher path loss. Higher path loss means the coverage is lower, is smaller. The higher frequency also imply they can have higher data rate because according to channel capacity theorem, we can have your data rate capacity is proportional to your bandwidth. High frequency also refer to shorter wavelengths. It means that you can have more antenna per unit area. So that's why massive MIMO become possible in 5G. So this is a simple characteristic between the frequency and the the wavelengths, you can see that around 300 megahertz, the wavelength is 1 meter. When you move to 3 gigahertz, the lambda drop to 10 meter. So when you about reach 30 gigahertz, it's 1 centimeter. So all the frequencies, when they move up to more than 30 gigahertz, the wavelength is at a millimeter wave order. So we have mentioned if you want to have diversity gain, you need to use your antenna separation should be greater than half lambda. So the lambda will affect the number of antenna per unit area. So let's so one of the challenge for 5G is the bandwidth. So let's see how 4G deal with the bandwidth problem.
If there are any sure bet about the future of mobile, they are that the data usage will continue skyrocketing. By 2020, the number of subscriptions, which includes mobile broadband, mobile PCs, tablets, routers, and IoT devices, is expected to grow to more than 9 billion. Needless to say, new applications and services will require even higher data rates. This cannot be achieved out of the blue, right? Certain means will be required. MIMO and OFDM are two base technologies that will be enablers. Along with these, there are a number of other techniques and technologies such as carrier aggregation, coordinated multipoint, LTE relaying, etc., which will be employed to improve the throughput and coverage. Hello everyone, welcome back to the fundamentals of 4G. Today we will be discussing about carrier aggregation. Imagine a road is connecting two places. Now, as the number of people traveling increases, what do we do to serve the increased traffic? We add more lanes or construct flyovers. Similarly, in LTE, carrier aggregation is used to serve increasing bitrate demand. Here, bandwidth is increased by aggregating separate spectrum, thus increasing the bitrate and network performance. Here, each aggregated carrier is referred to as a component carrier or CC. The component carrier can have a bandwidth of 1.4, 3, 5, 10, 15 or 20 MHz. And as per 3GPP, a maximum of 5 component carriers can be aggregated. Hence, the maximum aggregated bandwidth is 20 times 5, that is 100 MHz. Now, carrier aggregation can be used for both FDD and TDD. In FDD, the number of aggregated carriers in downlink is always greater than or equal to the number of carriers in uplink. While in TDD, the numbers will normally be same for both downlink and uplink. Now, in LTE Advanced CA, each component carrier used for data transmission is also referred to as a serving cell. In carrier aggregation, we have multiple serving cells, but RRC connection will always be handled by primary serving cell. In idle mode, the UV listens to system information block broadcast message through primary serving cell and sends the uplink control information through the uplink control channel of it. Basically, all signaling messages are handled by PCC. The other component carriers are all referred to as secondary component carriers or SCC. Unlike PCC, there can be multiple SCC. The SCCs are added and removed as required, while the PCC is only changed at handover. Introduction of carrier aggregation introduces new messages in the protocol layer. Here, some new RRC messages are introduced to handle the SCC. MAC must be able to handle scheduling on a number of component carriers. Regarding scheduling, there are two main alternatives for carrier aggregation. Either resources are scheduled on the same carrier as the grant is received, or so-called cross-carrier scheduling may be used. In physical layer, the signaling information about scheduling on component carriers must be provided in downlink, and HARQ ACNAC per component carrier must be delivered in uplink and downlink. Now, the aggregated carriers can be intra-band contiguous. This simplest CA deployment scenario aggregates multiple adjacent component carrier in a single operating band. However, in most countries, the spectrum allocation is more fragmented and contiguous aggregation within the same frequency band may not be possible. For such scenarios, non-contiguous CA is deployed. The main advantage of LTE is it can be deployed in various frequency bands. And to serve huge customer base, operators have license to operate in multiple bands. To aggregate component carriers from different frequency band, the operators deploy interband CA. Interband CA is more complex than intraband CA because the multi-carrier signal cannot be treated as a single signal and therefore requires a more advanced transceiver in the user equipment. To specify different CA combinations, we need to understand some new definitions. Number 1, Aggregated Transmission Bandwidth Configuration, or ATBC. It is the total number of aggregated physical resource blocks. Number 2, CA bandwidth class. It indicates a combination of maximum ATBC and maximum number of component carriers. In release 10 and release 11, three classes are defined. Class A, it has ATBC less than 100 and maximum number of component carriers is equal to 1. Class B has ATBC less than 100 but maximum number of component carrier is 2. Class C has ATBC ranging from 100 to 200 and maximum number of component carriers is 2. The third one is EU-TRAN operating band. It refers to the chunk of frequency allocated by ITU to deploy LTE in FDD or TDD modes in different parts of the world. For example, band 40 refers to TDD operation in 2300 to 2400 MHz range. Now, CA configuration indicates a combination of EU-TRAN operating bands and CA bandwidth classes. To exemplify, the configuration CA40C indicates intra-band contiguous CA on EU-TRAN operating band 40, that is 2300 MHz, and CA bandwidth class C. CA3A3A indicates intra-band non-contiguous CA on band 3, that is 1800 MHz, and CA bandwidth class A. Finally, CA3A5B indicates interband CA on operating band 3, that is 1800 MHz with bandwidth class A, and operating band 5, that is 850 MHz with bandwidth class B. To support CA, mobile device manufacturers must deploy capable CA products. In LTE, user equipment categories define the capabilities of a mobile device. After the network has identified what category a mobile device supports, it knows the device capabilities and can scale the data link accordingly. In 2011, intraband contiguous CA was introduced in 3GPP release 10. It was limited to 2 CCs and maximum aggregated bandwidth of 40 MHz. In 2013, the 3GPP Release 11 expanded the deployment options and capabilities of CA. It introduced intra-band non-contiguous aggregation and support for multiple time advances, that is, cells belonging to two different sites. In 2014, 3GPP Release 12 was completed. Uplink interband CA was defined in this release. Requirement for 3 component carriers in downlink and 2 component carriers in uplink was also defined with maximum aggregated bandwidth of 50 MHz. In future releases, licensed assisted access and 4 downlink carrier aggregation has been planned. In 2013, the first commercial implementation of CA was deployed in South Korea, followed by UK. Australian mobile operator Optus was the first to deploy CA on a TDD LTE network. CA technologies has since been deployed on LTE networks in regions throughout the world, notably in the North America, Japan, China, and India. From device point of view, the main advantage of CA it can be used to provide a bandwidth of up to 100 MHz, which means user can get more data rate. However, CA operation requires more receiver activity and more processing, so the power consumption is higher. From network operators' point of view, CA can be used to club fragmented bandwidths, thus ensuring greater bandwidth utilization. It supports cross-component carrier scheduling, where the control channel at one carrier can be used to allocate resource at another carrier. Thus, it is a powerful technology for effective utilization of radio resources. From release 11, it is possible to handle CA with component carriers from different sites. So, macro base station with full coverage could provide system information and RRC control signaling, and small cells and picocells would serve high data requirements. So friends, we have seen how network capacity is enhanced using carrier aggregation. In our next video, we will discuss how coverage is improved using heterogeneous network.
Okay, let's come back. So here we try to briefly summarize the concept for carrier aggregation. Actually, that's the technique we use in 4G to achieve a higher data rate. So EMBB is already ongoing since 4G. So this is the concept for carrier aggregation. Originally, we mentioned that for LTE, the channel bandwidth can up to 20 MHz. This is a requirement for LTE. In order to further enhance the data rate, they propose carrier aggregation. They start to use carrier aggregation to provide higher bandwidth. To 5G, we have mentioned 5G, they have non-standalone, means you can use 4G bandwidth and the 5G bandwidth together. In 5G, NSA, they also provide concept, they call it dual connectivity. In dual connectivity, you can also use the concept of CA, use multiple bandwidths. But the major difference is dual connectivity, you will use the frequency band from 4G and the frequency band from 5G, because in NSA, the user can connect to two kinds of base station simultaneously. So this is a term used in 5G. This is a term used in 4G. Actually, their main purpose is to use a wider bandwidth. So let's quickly go through the 5G standard. Actually, there are some important milestones at the end of 2017. They start to define freeze release 15 standard. This is the first standard for 5G we just mentioned. The first standard actually they support non-standalone. Half a year later, release 15 further define the standard for standalone. This is pure 5G network. To the end of 2019 is release 16. Now is around the end of release 17. So parallel wireless, they summarize the key difference. Release 15, part 1 is for non-standalone, part 2 is for standalone. And they have a final version. The first release in release 15, actually the main focus is for eMBB. For 16 and 17, they focus on UILC. Up to now, actually they don't spend too much time for massive NTC because currently in LT they have an NB-IoT standard. Also we mentioned massive NTC, they want to have much more in device, but with lower data rate. So data rate is not a concern here. So they still use try to enhance existing NB-IoT standard. So here is a list of 5G standard. You may find that actually they have the same naming rule. For 3G, all the standards start from 25. It's a 25 series. For 4G, become 36 series. For 5G standard, you need to refer to 38 series. For example, there are some important standard. First one, physical layer, 2 series. They have normally the standard they have 3 digits. 0, series 0 normally provide a general description or overview. 1 series with 1, 211, 212, 13, 145, 15 is a physical layer standard. They define the channel modulation and multiplexing in channel coding. Professor Nana just mentioned yesterday. They also have physical layer procedure for control channel, for data channel. And since the handset need to measure the signal for the base station, so they also define a physical layer measurement related procedure. So this is 38.2 series. The 3 series is related to radio protocol. We will spend more time to describe this part in the rest 3 days. The same 38, 1 series is for general requirement, then physical layer, then radio. 0.4 series is more about the network architecture and the interface. As we mentioned, in 5G, they can have 2 network operation mode. One is NSA, another is SA. NSA means 4G base station, 5G base station connect to 4G core network. SA means 5G and 4G enhanced base station connect to 5G core network. So both of them, they need to support control plane and the user plane information. I'll quickly go through the release 16. 16, actually, they define two parts. The first part, they want to address balance of between efficiency and expansion. First of all is expansion, they extend. As we mentioned, release 15 is more related to eMBB. So release 16, they try to define some extra feature for 5G. For example, V2X, 5G V2X is to support self-driving car. They try to define industrial IoT, IIoT, to support massive URLC application. They also define some feature to enhance URLC. As you see in the last part of the video, they mention LAA. So-called LAA actually is they try to use unlicensed band for 4G. So in 5G, they also have 5G unlicensed spectrum operation. They want to use frequency band reserved for Wi-Fi to enhance the standard. You can also find that they still have some other progress. First one is 5G for satellite. Now may become the fundamental for the 6th generation. They call it next generation non-terrestrial network, NTN. NTN is the term they use for 6th generation for satellite communication. To further increase the data rate, they need to go to higher bandwidth. So they also consider above 52 gigahertz band. For efficiency, they try to do interference mitigation, try to reduce the interference among the base station. They try to use big data to do SON, self-organized network. They also try to do enhancement 5G. Power consumption improvement, dual connectivity is a DC I just mentioned. You can use two base station, one user connect, one device connect to two base station. What we mentioned is the concept is want to increase the data rate is one of the option. Actually, they also have another option that can be used to increase the reliability of the network. So quick summary, 5G new radio, they can provide a scalable numerology. Numerology actually is the different carrier spacing mentioned by Professor Nana yesterday. So you can use different numerology, different subcarrier spacing, so they can have different slot duration to adjust the requirement. So whenever you can use a higher bandwidth, you can use a smaller slot. So you are able to reduce the latency. You can also assign use dual connectivity to achieve enhance the reliability. They also introduce beamforming, channel coding. Professor Nana just mentioned yesterday. After check, we confirm that LDPC is for in 5G for data channel. They originally they also discussed to use polar code for data channel, but now according to the standard is LDPC for data channel, polar code is for control channel. Because control channel need to have more reliable transmission, it's also show smaller block. Another concept is they want to have flexible and modular RAN architecture. They want to split the Fronthaul. They also want to split control and the user plane. We will mention later. Due to this nature, if you are able to do this, you are able to support network slicing. So DMA has been introduced by many professors in the past few days. If you are interested, you can also check it by yourself. We can skip here. The concept is you can have different subcarrier with subcarrier spacing. Here, I just want to mention in LTE, they used 12 subcarrier and one slot. Here, this block is the unit for their resource allocation. They call it resource block. So you can see that they did not allocate resource per subscriber, but they allocate resource for a number of subcarrier. In here, in 4G, the subcarrier spacing is 50 kHz. But as you know, Professor Nana just mentioned, we can have 30 kHz, 60 kHz, 120. When you increase the data, increase subcarrier spacing, you increase, for example, you double it from 15 to 30. So the same amount of data can be transmitted during half of the time. So you are able to shorten the slot duration. So that's the major concept for 5G. So this feature, massive MIMO already mentioned, new channel coding already mentioned, scalable of DM already mentioned yesterday. So this is the concept for scalable. So you can change the subcarrier spacing. When you change the subcarrier spacing, your channel bandwidth can be enhanced. At the same time, when you increase so this is for 50 kHz subcarrier spacing. So this is 1 millisecond subframe in LTE. So in LTE, 1 millisecond subframe. In 5G new radio, the radio frame is the same as LTE, 10 milliseconds. The subframe is the same as LTE, is 1 millisecond. Slot, one slot that is equal to 14 OFDM symbols. The 14 OFDM symbols, the duration of the symbol depends on the numerology, depend on the subcarrier spacing. So in here, this case, this 1 millisecond in 50 kHz subcarrier spacing, they have 0 to 13. So each one of them is an OFDM symbol. When you double the frequency, the duration is reduced from 1 millisecond to 500 microseconds. It still have 14 OFDM symbols. So when you increase the data rate to subcarrier spacing to 120 kHz, the slot duration can be reduced to 125 microseconds. Why this is important? Because in LT, the scheduling is based on slot subframe. So the scheduling interval is 1 millisecond. So whenever you move to 120 kilohertz, you are able to reduce the scheduling interval to 125 microseconds. So this is essential for UILC. For UILC, they want to have a very low delay between the mobile station and the base station. They want to have 1 millisecond, for example. To achieve 1 millisecond, you are not able to have 1 millisecond scheduling interval. So this is the feature defined for ultra reliable low latency. Due to this design, the allocation for the resource can be quite flexible. So you can reserve some wide bandwidth for eMBB. To certain situation you want to have ultra reliable low latency, you can occupy a very wide bandwidth in a very short period of time. So you can get the bandwidth immediately. So this is a MIMO already mentioned yesterday. Let's quickly check what's beamforming. Beamforming is very important. So
demonstrate how beamforming works on the 1250. Let's take a look at two element transmitters. In this demonstration, we're using the combined energy of both element transmitters to focus on a specific location. When the laptop moves, we can use beamforming to recalculate the energy so it moves along with the laptop. Now let's take a look at a skyward view of the radiating patterns from each element.
Excuse me, Prof. Ray. Maybe
yes,
this is not the video. This is still the slide,
You will see points in
the sharing one.
so
which they don't
you don't see the video.
See, yes.
Okay.
Now
So
it's still the 5G and air radio.
oh,
frame.
okay. Thank you for reminding. Let me
Okay.
check. Let me check again. So can you see my screen now?
Yes, it's okay
Yes,
now.
Prof.
Okay, thank you. Yes, please remind me. Otherwise, I cannot know.
Element transmitters to focus on a specific location. When the laptop moves, we can use beamforming to recalculate the energy so it moves along with the laptop. Now let's take a look at a skyward view of the radiating patterns from each element transmitter. As you can see, the pulses are identical from each transmitter. As the rings radiate out, you will see points in which they cross and in points which they don't cross. The points in which they cross create a phase amplitude, effectively higher signal at that location. The normal gray rings indicate standard transmission power from any one element. In this example, we will place a laptop in the non-beamforming pattern at a coverage hole location. Minus 80 dBm is normally the signal strength where connectivity is compromised. Now that we know the location of a coverage hole on a non-beamforming pattern, let's take a look at what happens when you use beamforming. As you can see, both transmitters again are transmitting, but the top transmitter is 10% out of phase with the bottom transmitter. This moves the crossover points, and as you can see, the crossover points are now directly at the laptop location. This virtually changed the signal strength at that location to move the laptop out of a coverage hole.
Okay, I think
Now let's take a look at how beamforming performs in an actual facility. Here we are zooming into
I think that's the main concept I want to share you. You can adjust the phase for the transmitter. Actually, the phase is the transmission delay. You can delay the transmission for each transmitter. When you transmit the same signal out, when you delay the transmission time, you are able to direct your signal to a certain direction. They call it beamforming. Beamforming is quite important in 5G. We just mentioned massive MIMO, you can have many antenna. So traditional in 4G network, you can have 3 antenna. Each one of the antenna, they serve one direction. When you have multiple antenna, for example, 64 by 64, you may have antenna to try to split the area into many smaller circles. So you can use the technology we just mentioned to focus your energy to a very small area. In this case, you can find 20 cells here. So in order to serve all of them, the concept originally you can see that you can divide a circle into 3 areas. Now, whenever you are able to divide into 20, so means your signal, your energy may focus to a very small area, so you can have a better service here. So this is the concept for massive MIMO. But the major challenge is how the base station know where the user is. So that's what they are doing in 5G. I just quickly go through the concept for beam sweeping. Beam sweeping is used to allow a base station to allow a user to notify the base station the base bit. So in this case, this is the time. We just mentioned the basic unit is frame. So at the beginning of some frame, they will send some broadcast message. This broadcast message is known as SSB. You don't need to know the term detail here, but you can just notify it's combine of broadcasting and the synchronization message. So at each time, they will show you they have many pins. So each one of them is related to a certain direction. So the base station will sweep the transmission pin to all the direction. So different user will receive better signal. For example, for UE1, you will find pin number 1 is good signal. UE2 find pin number 6 is good signal. So in this case, so the base station, they will sweep the pin. Then the user equipment, they will detect the best pin. They will know which one is better. For example, when UE1 find pin 1 is the best one, they will report to the base station at a certain time, which the time is reserved for pin 1. So base station knows when, according to when UE connect to the base station know which is the best pin selected by the UE. Similarly, they can do it for UE2. So this is pin sweeping, pin management. Okay, I guess we can have, it's about time to take a 10 minutes break. After come back, we will show you the system architecture. What we just mentioned is we show you the background knowledge. We try to provide some extra information we did not mention yesterday. Later on, we will show you the system architecture. Before that, Okay, maybe we can have a quick video first.
In previous generations,
see the
base
video?
stations were controlled by a central device. In 2G, it was the base station controller, and in 3G, it was the RNC. These controllers were responsible for setting up the radio links to wireless devices via the base stations, for controlling the connections while in use, for ensuring quality of service, and for handing over a connection to another base station when required. In LTE, this concept was abundant, as it required significant resources because the task was concentrated in few network nodes. Most applications on the device only transmit and receive information in bursts with long timeouts in between. During these times of inactivity, the air interface connection to the mobile devices has to be changed to use the available bandwidth efficiently and to reduce the power consumption of mobile devices. So, the packet switch connection generates a lot of signaling load because of the frequent switching of the air interface state. So, these management tasks were distributed to speed up the connection setup time and reduce the time required for handover, which is very crucial for real-time services, thus making the LTE access network a simple flat network of interconnected base stations without a centralized controller. Hello everyone, welcome back to the world of LTE. Today we will discuss the radio access network of LTE, which is also called Evolve UMTS Terrestrial Radio Access Network or UTRAN. The most complex node in the LTE network is the base station, referred to as eNode B. It is derived from the name which was originally given to the UMTS base station Node B, with an E referring to Evolve. eNode Bs consist of two major elements. RRU, or the remote radio unit, consists of the antennas. It is also called remote radio head, which are the most visible parts of mobile network. They are also responsible for modulation and demodulation of all signals transmitted or received on the air interface. The second part is BBU or baseband unit, which consists of digital modules that process all signals transmitted and received on the air interface and acts as an interface to the core network over a high-speed backhaul connection. Now in LTE, base stations are autonomous units. Most functions of the RNC were integrated into the eNode B. Hence, the eNode B is not only responsible for the air interface but also for radio resource management that includes radio bearer control, radio admission control, connection mobility control, and scheduling. There is dynamic allocation of resources to UEs in both uplink and downlink. It is also responsible for IP header compression and encryption of user data stream, selection of an MME at UE attachment when no routing to an MME can be determined from the information provided by the UE, routing of user plane data to a service gateway, scheduling and transmission of paging messages originating from the MME, scheduling and transmission of broadcast information originated from the MME or ONM, measurement and reporting configuration for mobility and scheduling. Now, the interface between the base station and the core network is referred to as the S1 interface. It is usually carried either over a high-speed copper or fiber cable or alternatively over a high-speed microwave link. The S1 interface is split into two logical parts, which are both transported over the same physical connection. User data is transported over the S1 user plane part of the interface. IP packets of a user are tunneled through an IP link in a manner similar to the already described for GPRS to enable seamless handover between different LTE base stations and UMTS or GPRSH. In fact, the GPRS tunneling protocol GTP is reused for this purpose. Only the destination IP address on layer 3 is changed, while the user's IP address remains the same. The S1 control plane protocol, as defined in 3GPP, is required for two purposes. Firstly, the eNode B uses it to interact with the core network for its own purposes, that is, to make itself known to the network, to send status and connection keep alive information, and for receiving configuration information from the core network. Secondly, the S1CP interface is used for transferring signaling messages that concern the users of the system. For example, when a device wants to communicate using the LTE network, an individual logical connection has to be established, and the core network is responsible for authentication, for supplying keys for encrypting data on the air interface, and for establishment of a tunnel for the user's data between the eNode B and the core network. Once the user's data tunnel is in place, the S1CP protocol is used to maintain the connection, to organize a handover of the connection to another LTE, UMTS or GSM base station as required. In S1CP protocol stack, instead of the commonly known TCP and UDP on layer 4, the telecom-specific Stream Control Transmission Protocol (SCTP) is used as defined in RFC 4960. It ensures that a large number of independent signaling connections can be established simultaneously with in-sequence transport, congestion management, and flow control. Now, as mentioned earlier, unlike the previous generation technologies, LTE integrates the radio controller function into the eNode beam. This allows tight interaction between the different protocol layers of the radio access network, thus reducing latency and improving efficiency. Such distributed control eliminates the need for a high availability, processing intensive controller, which in turn has the potential to reduce cost and avoid single point of failure. One consequence of the lack of a centralized controller node is that as the UE moves, the network must transfer all information related to a UE, that is, the UE context, together with any buffered data from one eNode B to another. So, to avoid data loss during handover, X2 interface was introduced. In LTE, base stations can communicate directly with each other over the X2 interface for two purposes. First, handovers are now controlled by the base stations themselves. If the target cell is known and reachable over the X2 interface, the cells communicate directly with each other. Otherwise, the S1 interface and a core network are employed to perform the handover. The second use of the X2 interface is for interference coordination. As in UMTS, neighboring LTE base stations use the same carrier frequency. There are areas in the network where mobile devices can receive the signals of several base stations. If the signals of two or more base stations have similar strength, the signal of the base stations that the mobile device does not communicate with at that moment are perceived as noise, and the resulting throughput suffers significantly. As mobile devices can report the noise level at their current location and the perceived source to their serving base station, the X2 interface can then be used by the base station to contact the neighbor base station and agree on methods to mitigate or reduce the problem. So friends, in this video we have seen how limitations of previous generation were mitigated by decentralizing the radio access network in LTE. In our next video, we will be discussing about.
Okay, so we can have the 10 minutes break. We can come back in 10:06. 10:06. If you have any question, you can write down on the chat room. Okay, I think it's about time for our lecture. So now we just quickly go through the background knowledge for eNode B. For 5G, they have a similar architecture as 4G. They have UE. They have UE, they have base station, they have core network. So you can have the major difference we just mentioned in the previous video. We will find MME is for mobility management. MME in 5G, they will be replaced by AMF and UPF. So basically, we can have 5G core and 5G next generation RAN. So this is the protocol stack. For that, you already see the GTP. You already see the SCTP. This is used for the transport protocol for control plane and for user plane. The upper part is for user plane. The lower part is for control plane. So today we will focus more on the GNOB side. So for user plane, they have SDAP, PDCP, ILC, and the MAC. For control plane, they have RRC, PDCP, ILC, and the MAC. So this is the base station. This part is the core network. So we just see that in LT, they call this S1 interface. But in 5G, this is N3 interface for user plane, N2 interface for control plane. This is the network architecture we just mentioned. We have base station, we have MME. This is for mobility management. We also have HSS. This is for user database. All the authentication and control is here. The serving gateway is the data plane. So whenever you have data, UE will transmit to base station. The data will go through serving gateway, then P gateway, then internet. But when you want to set up a connection, before you transmit the data, you should go to MME. Whenever you move from one base station, one node B to another node B, is also controlled by MME. We just mentioned in the previous video, we know node B is to deal with radio-related function. They are responsible for radio resource management, header compression between the user, because this IP packet, the IP packet is redundant during this part, so they will do some header compression. They also deal with security issue. They also want to connect to the EPC. Here, this is the core network. In 4G, is EPC. MME is a mobility management entity. This is main control entity in LTE network, core network. They are dealing with authentication, mobility management, location update for mobility management, barrier establishment, handover control. HSS is a home subscriber server. It's a central database that keeps the user profile. It provides the user authentication information and the profile to MME. So real user information is kept in HSS. We will briefly summarize it on Thursday for the security part. We also have PCIF. PCIF is policy and the charging rule function. It makes the policy decision for each and the QoS setting and charging rule to the P gateway. So actually, PCF keep all the user subscription information. So based on the subscription information, they can use it to set the policy and the charging rule for each user. So accounting information is handled this here. So this is for 4G. This is for 5G. it seems more complicated than previous one, but actually the function are quite similar. We just mentioned we have InnoB here, but this one is UPF. UPF is a user prem function. Basically, the UPF, the function is similar to the serving gateway. They have MF. MF is access and the mobility management function. Is similar to MME in LTE. They are handling access authentication, mobility management control, support of network slicing, and session management, selection, SMF selection. SMF is a session management function. It extracts the section management related function from MME. So actually here, this two is originally MME. Why they split into two parts? They want to do control plane and user plane separation. So the user related information is handled by SMF. The mobility related information is handled by MF. PCF is similar to the PCF we mentioned before, so they changed the name. NSSF is a network slice selection function. It's used to support the network slicing function, which is quite important in 5G, which is not support in 4G. So this is the new function. AUSF is an authentication server function. UDM is a unified data management. So what we talking about the HSS keep the user database. They also be responsible for the authentication server. So actually, this is the HSS we consider in 4G. Here we have another new entity. They call it application function. Actually, the function for application function is our scope. Within this side, all the components are well defined by 3GPP standard. For AF, actually, this is an application function. It's a server provided by the user. For example, if you are Tesla, you want to have self-driving car, you have your own application to control the speed control, provide the roadside information, even provide the map. You can use AF. So AF can be customized design for self-driving car, for industrial IoT, factory automation. So all they need to do is they can follow this interface and fine. They can support their service. We mentioned a lot. We use this figure to show you what are the main concepts they are using. This is EPC. EPC is for 4G. We just mentioned in 4G, we have control information through the MME. This is a subscriber database. We also have PCF to charge the user, set the policy, set the charging for user through the P gateway. So what they are doing today, first one, they do so-called CUPS. CUPS, they try to, this one is a control plane functionality. So they try to split MME into two parts. They try to split the function of MME they try to split the function of serving gateway. Even for the serving gateway, even they are transmit the data, actually they have control plane and the user plane. So they try to split the function. CUPS is separate the control plane and the user plane. They do control plane and user plane separation. So this is control user plane separation. So they try to split the control information. MME already be control information, but serving gateway, they contain the control information and the user plane information. So each user plane is only for router. Control plane function is to setting the routing path. The same, they split P gateway into control plane and the user plane. What's the meaning for control plane? Actually, they can map to EPC to 5G. So originally, MME, they have function is in SS control. So they map to AMF. Part of the function, control function related to session management, they will move to SMF. Both of the control function related to session control is originally is a control plane for serving gateway and P gateway. Now they also combine to SMF. What's the UPF? UPF is the user plane part for packet gateway and the serving gateway. PCF remain the same. They rename it as PCF. HASS is a user database. In 4G, they also have AAA center. So the AAA center is related to authentication. So they will move to AUSF. HS, the database, they will move to UDM. So it's the major concept for the 5G core network. So we can have quick comparison. Upper part is 4G, lower part is 5G. So this is data plane. Normally, this is the user plane. This is the control plane. And here is the same user plane. All of them are related to control plane. So we can find that in 5G new radio, the MME, they split some function in MM, some function is SNF. PCF, PCIF is corresponding to PCF. HSS is corresponding to AUSF. But we know for SMF is also consider some of the function for UPF, some of the function for serving gateway control plane and the packet gateway control plane. So this is 5G architecture. It's also complicated. They have many interface. One interface is defined for each two components to exchange the information. So this part is still complicated in 5G. To simplify a concept, they proposed service-based architecture. So it means they want to use service-based interface. For example, they can use HTTP-based architecture to allow all the others to use this architecture to exchange information with the others. So the bus become a simple massive message bus. So everybody can use the message bus to exchange information with the others. So up above is the control plane part. The lower part is the user plane part. So all of the terms are defined here. So this is the 5G system architecture. So then we summarize in RAN architecture, we have core network, we have base station. The base station can further split into CU and the DU. We will mention the functional split later. So base station, we just mentioned in LTE. In the video, you can see the S2. In 5G, they call it SN interface. NG is an interface between the base station and the core network. F1 is the interface between CU and the DU. For the deployment, basically, we can see the core network, you can have 4G core, 5G core. Base station, you can have the operation mode, you can have SA or non-SA. Non-SA means you will have two types of base station connect to the single core network. So the core network, if the 4 is EPC, so this one, the option 1 is 4G. Option 2, option 3 here actually is the non-standalone for 5G. So this is the first option if you already have LTE network. Then your EPC will upgrade to 5G core. So you will use 5G core to connect the base station. If you use 5G core to connect the 5G base station, it's option 2. If you use 5G core network to connect the 4G base station, it's option 5. You can also have a 5G core network to connect both 5G and the 4G base station. This is referred to as NSA. They can have option 3. Option 3, so when you have option 3, you can replace the EPC by 5G core. So they can upgrade to option 7. Or you can just replace this one, they can upgrade. Or the LTE network, you can upgrade to option 5. So they have different migration paths. But here, I just want you to understand, you can have 4G core, 5G core. You can have single standalone, means one type of base station, or you can have non-standalone, a hybrid of 4G and 5G base station. So here is the part we summarize the 5G standard from the radio part, from the network part. Now we will move to functional split and the ORAN Fronthaul interface. Contributor is Jonathan and Kevin. Kevin is a student from OFI who take the TEP intern. The outline is we will split into 2 parts. The first part is a functional split. Actually, for this part, we already briefly summarized in the first day afternoon course when we are talking about the ORAN alliance. But we will show you more detail here today. Second part is ORAN Fronthaul interface. So let's check it one by one. Functional split. We know, we already mentioned from the PC area, we start to have a commodity hardware, then we try to have different OS to the RAN. Actually, they also want to do so-called hardware and the software disaggregation. What do we mean by disaggregation? Is traditionally we have base station, we have core network. So you need to buy a machine from Nokia. Nokia provide the hardware plus the software. It's just like if you want to buy a server from somebody, you need to buy all the software from the server's vendor. When we start to, so this is all-in-one. This aggregation, they try to split hardware and the software, They try to split it. Why? If you can split it, you can buy hardware and the software from different vendors. So you already see this figure in the video. Just mentioned you can have RU and the BBU. Or everything we talk about the signal processing is handled by the BBU. Or most of the protocol we mentioned today is also included in the BBU. So now they already split this radio part and the BBU part. Both of them, they can be interconnected through the RF cabling or fiber. So they can use RF part as pure hardware. They implement everything in ASIC here. But for the base station part, they still need to have hardware plus software. The purpose of Open RAN is they want to disaggregate the hardware and the software. So they have some concept. The first one, they want to use open interface. Also, we just mentioned the interface for, you can find that here. Even they can use the CPI. CPI actually is the frame format to transmit Ethernet packet through the fiber. You can use the CPI protocol to transmit, but how do you map your symbol to CPI? Actually, it's not well defined. Actually, it's a proprietary. It's vendor specific. As we mentioned, one of the important issues for ORAN is they want to have open interface. When they want to have an open interface, the hardware part, they can be they can still try to use the general processor with commercial hardware to do this. For the baseband unit, they also want to have a commercial server, commercial hardware, plus either open source or proprietary software. So this is a stack we just mentioned. So what we do, we already mentioned you can have distributed RAN to centralized RAN, even to cloud RAN. So what we want to decide is, this is the protocol from the base station. What we want to decide is how do we split it. So one of the options is origin we can have is we split the radio unit and the baseband unit. So we split it into RU and the BBU. Then what we can do is we also can do CUPS, control and the user plane separation. The concept already be introduced in 5G core network. Then they can introduce the concept to the 5G RAN. So they can try to split the function in 5. So for 4G, from 4G to 5G, first of all, let's define functional split for CU and the DU. They also define the functional split of CU into control plane and the user plane. So here on this video, they can have two split. The first one is vertical split. This is the C control plane, user plane split. The second one is horizontal split. They split the CU and the DU. So this is original one before split. After the CU-DU split, they split the BBU into CU and RU. Then we have 3 turns: backhaul, midhaul, and the fronthaul. Backhaul was used to connect the core network and the CU. Midhaul is between CU-DU using F1. Fronthaul is between DU and RU. So we can have quick comparison between CUPS and the CU-DU. CUPS is vertical split. CU-DU is horizontal split. So CUPS is the first step to introduce SDN to a RAN, software-defined networking, to radio access network. They try to separate CU into control plane and the user plane. So they can have consistent control plane in multi-vendor network. So you can encourage multi-vendor support for the base station. It's more simple in higher layer, but more challenge for lower layer. CU-DU, they try to want to have a centralized scan in terms of performance and the scale. They try to shift functionality to different location in order to support different service. As we mentioned, you can have, when you want to have UILC, your user plane handling function may be moved to the user side, to the edge, to reduce the latency. They also try to reduce the cost of RAN by using commercial available hardware. Here is the split function, 3 split function. So you can have higher layer split. You can also have lower layer split. Higher layer split is the CU-DU split. So this is defined in 3GPP. They define higher layer CU. They define lower layer. This is DU. So the RU actually is part of the DU. In ORAN Alliance, they define the lower layer separation. So for example, here is the split 7.2. So this part is CU plus DU. This part is radio unit. So you can have different option for the split. According to the standard, they have different option. Option 1, 2, 3, 4, 5, 6, 7, 8. Higher value refer to the physical layer. Professor Nana already introduced, when you want to transmit, you will have protocol. Then you will go to FEC, channel coding. Then due to try to prevent from the burst error, you will scramble the packet. Then you can do modulation, layer mapping. Layer mapping is when you provide multi-user MIMO, you want to transmit or you want to provide multiple antenna, you want to transmit different bit to the same user. So you need to know which the information is transmitted from which antenna. So you need to do layer mapping. You also need to do pre-coding to map the symbol to antenna. So this is for MIMO. Then you do resource element mapping, IFFT. This is for transmitter side. Then you can do DA conversion, then transmit to antenna. So you can have different options. Option 1 is about PDCP. Option 2 is between PDCP and RILC. Option 2 is now used for F1 interface. We already used defined in 3GPP. So this one has been chosen for higher layer split. Traditionally, the separation of BBU and RU is based on option 8. So this part is RU or RH. In ORAN, they define a spec based on 7.2. 7.2 is in resource element mapping. So this is a figure show you what are the options we can have. We can have split A. Split 2 is between CU and the DU. This is a F1 interface we already have. When we follow, so this standard defined by ORAN Alliance. They, in addition to F1, split 2, they follow define split 7.2. So it is this part. Split 7.x means they try to have a separation. They separate the file into two parts, the high file and the lower file. So this is another view for this part. So actually we can use, so this is high layer. So if you want to have a split above the MAC layer, they refer it as a higher layer split. If you want to have split for the physical layer, they call it lower layer split. So here are options. We don't go into detail, but we show you the trade-off in the higher layer split. So basically, you can consider it from Fronthaul point of view, from functionality point of view, from capability point of view. If you have a higher layer split, means more function is implemented in lower layer. So higher layer is more simple. So if you just transmit the data between PDCP and the RLC, the data here to be transmitted is the PDCP packet. The amount of PDCP packet actually is small. So from Fronthaul point of view, higher layer split, the data rate is smaller. when you want to move more data to the lower layer, for example, here between the Mac and the file, actually is still the Mac PDU. But if you want to spread physical layer, maybe you need to transmit bits or symbols. The bits and the symbol originally they are transmit within your CPU, so they can have they are close to each other. They can use a very high speed to transmit. But now you want to spread it, so you need to transmit through the fiber Ethernet. So the data rate for the fiber Ethernet will be greatly increased. So if you want to transmit for the physical layer and the RF, means you need to transmit the IQ signal either in time domain or frequency domain. Both of them, you need to transmit it. The bandwidth requirement is higher. Here is whenever you want to do comp. Comp is coordinate multi-point transmission. You want to have multi-base station to transmit the same content. It's more easy to do it in higher layer. For example, if you want to, when we want to use PDCP, we can transmit the same PDCP packet through two different base stations. So when you want to combine the packet, you only need to choose which of the PDCP from RU1, from RU2, or RU plus DU1 and the 2. You just choose the one with lower, with the correct one. You only need to select the correct one. It's quite easy for you. But if you want to do it in the physical layer, you need to get an IQ from two base stations, and you need to decide which of them is good. Then you need to combine it. The effort is more complicated. Similarly, you want to support the density in the higher layer spread. You can support less. But if you can do it in lower layer, you can have better performance in the physical layer. So you can have better performance. You can support more users. So they are the spread option for lower layer. So you can also have some similar trade-off in lower layer spread. In lower layer, let's go through it one by one. For lower layer means we want to have spread in the layer 1 in the physical layer. Yesterday, Professor Nana just showed us all the transmitter trend. We want to have encoding. This is channel coding, then scramble. Then you can do modulation, layer mapping. You want to map the symbol to different antenna. For each antenna, you need to do pre-coding. You need to adjust the weight. We just mentioned if you want to do beamforming, you also need to transmit the weight for each antenna. You need to know how to adjust the phase for each antenna. Then you map resource to the resource element. So this is a resource element mapping we just mentioned. In LTE, the resource element actually is a subcarrier times a symbol time. So it's map all the resource to each symbol. So you can do so-called digital beamforming, analog beamforming. So whenever you want to do the beamforming, you need to adjust the weight. The pre-coding is to code the the antenna to add a special code for the antenna. If you want to do beamforming, you can also introduce the beamforming to add some factor to control the phase of each antenna. Then you will do IFFT, then you do analog to digital to analog conversion, then you can transmit to the antenna. So similarly, they have a similar requirement when you want to do the lower spread in the lower part, you need to have a higher bandwidth. If you but if you can do it more here, the RU will be simple. When you spread it in the higher part, the RU will be more complicated. And here they also describe whether it's easy to implement a RU or DU. Before end, we just mentioned about the beamforming. Okay, I guess MIMO we can just skip it. Here is a table show you the required bandwidth and the latency. I just focus on the bandwidth. We show you when you spread it in lower layer, the required bandwidth will be increased. But we forgot to mention, if you do the spread in a higher layer, the delay, the latency will be increased because you need to, all the decision, you need to go through the higher layer to make decision, then you will have introduce a higher latency. So this figure briefly summarizes the data rate required for CC4 by CC4 massive MIMO with 100 megabit, 100 megahertz bandwidth. So you can find that if you spread number 6, spread 6 is between the MAC and the PHY. So all this requirement actually is related to lower layer spread. So the backhaul, the fronthaul requirement will increase from 3 giga to 4 giga if you use 77.3, 7.2. You will find different definition for spread 7.2. So if you use spread 7.2, you require 20 giga. If you move to 7.1, you will increase to 140 gigabits. But if you use spread 8, totally spread the RF and the DU, you will need 236 gigabit per second. To remember, the bandwidth is for 100 megahertz. If you want to use 400 megahertz, your data rate will be significantly increased. So actually, this is the trade-off for fronthaul selection. Okay, I think it's almost time. Okay, let me finish this part. So different spread, you will find different the protocol. Actually, they are the same. They just want to spread into 2 parts and they interconnect them through the fiber, the fronthaul. So they show you delay requirement. If you do separation in spread A7, the delay is around 100 microseconds in one way. But if you want to do it in spread 6 and 5, you need to increase the delay to 0.5 millisecond to 1 millisecond. But if you want to do it in PTCP because PTCP now is in CU. CU can be put in the core network. The delay will be much more increased. Here is a requirement for user throughput. So this is an example from Nokia. They show you the different option. So for the first version, for millimeter wave, they put CU. This figure is upside down compared to the previous figure we show you. They have CU and they put DU and RU all together because we just mentioned the Fronthaul, the data rate will be very high, especially you consider the millimeter wave. For millimeter wave, the data rate, the bandwidth is much higher. So they suggest they have the first version for the VRAN, the Cloud RAN. They try to do CU and the DU split. So this is the proposal for 3GPP. Then you can have a different option. You can have CU, DU put together, and RU put in the remote. For lower bandwidth, it's more possible because the Fronthaul, you are able to support the Fronthaul with a higher bandwidth because the bandwidth, the channel bandwidth for sub-6 or mid-band is slower, is more smaller. But what they are doing is they try to use in DU, they try to use CPU plus some accelerator to implement the Cloud RAN architecture. Even more, they can try to use DU plus with GPU. GPU, they can use as an accelerator to simplify. For this part, they try to reduce the cost for DU. Okay, I guess it's about time to have a break. It's now 54, so we can come back at 11:04 in Taipei time, 10:04 in Jakarta time. Okay, let's come back. We just mentioned we have different split option, but we need to understand the split also will affect the radio resource management. Here's an example show you different radio resource management function. So if you want to do something, it's also related to the decision. It will also affect the decision. So normally, central radio resource management located at the CU, they can use to coordinate the lower layer function across multiple DU. The general functionality of RM are radio resource allocation, call admission. Here, actually, is the cell selection, call selection, load balancing. You can select a different base station to handle the call. Mobility, multi-connectivity. So the max scheduler is the most important part for RM. They need to know the context information to fulfill a user's QoS. They also need to adjust the TTI. The TTI is a time transmit. Now, transmit time interval is a basic unit for scheduling. So since 5G define a flexible numerology to support different service, so you need to combine everything together. So the max scheduler is very challenging. Sometimes you also need to consider so-called punctual or preemptive scheduling. For example, if you want to have a UILC, we just give you an example. When you want to have UILC, you have emergence control, so you need to preempt the scheduling, then allocate to UILC user. So this figure conclude the difference between 4G and 5G. 4G we call it baseband unit and RU. Now for 5G, we split into CU, DU, then RU or AAU. AAU is the antenna unit. So this is the functional split use. We just show you we have different options. But this is the function we define in ORAN. F1 is the split 2. It was defined in 3GPP. For ORAN, they have ODU, but they split ODU into ODU high and ODU low. The interface between ODU high and low is a FAPI interface. Third one is a split between ODU and ORU. This is open Fronthaul interface, OFH. They can have user plane, control plane. So this is the FAPI. FAPI is an interface between layer 2 and the layer 1. FAPI and FAPI, both of them are defined by small cell forum. The major difference is when you want to split it into 2 hosts, you need to use FAPI. If the layer 1 and layer 2 running on the same host, you can use FAPI. Here, I just want to point out, they just in ORAN Alliance, they use P5 and the P7. P5 actually is for control plane. P7 is for user plane. So this figure shows us the different split action option. Split 2 is a phone interface. Split 6 is a FAPI or unFAPI they use to split MAC and the physical layer. Fronthaul interface, they define 7.2 split. So this is ORAN Fronthaul. So in the last hour, I will quickly go through the Fronthaul interface defined by ORAN Alliance. We show you this figure, but here we just want to tell you the split option 7.2 actually is here. They define in resource element mapping. So the high-fi and the low-fi are separate by resource element mapping. So in our reference, we have a paper from Docomo, NTT Docomo. The title of the paper is Overview of ORAN Fronthaul Interface. You can see all the detail we mentioned today in this paper. So the Fronthaul is, we have CU, DU, RU. From protocol point of view, CU is running PDCP, and SDAP is for control, user plane, or PDCP plus RRC is for control plane. So this is control plane, this is for user plane. PDCP is used in both parts. ODU is ILC, MAC, and Hi-Fi. Hi-Fi just ended in resource element mapping. So here is the step is like this. Encoding, then scrambling, modulation, layer mapping. This order is a little bit confused. So you can check this figure for detail. All the background knowledge has been mentioned by Professor Nana yesterday. So what are the important functions for Fronthaul? They want to transport data between DU and RU. They propose a split function between ODU and ORU. They also can enable multi-vendor RU and the DU interoperability. Since they actually this is the split is in more close to the higher layer part of layer 1, so it also can increase the transmission bandwidth. Downlink, they also handle downlink uplink. We have mentioned CPI. CPI actually is a common public radio interface. This is but the problem is existing CPI interface. Their implement is vendor specific, so it's not possible to do interoperability of DU and RU. Fronthaul interface. The Fronthaul interface defined by ORAN. They want to support open Fronthaul. The main purpose is to achieve multi-vendor operation interoperability. Fronthaul interface actually is a protocol. Actually, is a protocol, not a signal processing technique. This is a protocol. They want to connect BBU and RH. They carry signal along the base station and the antenna using fiber Ethernet. So this is the Fronthaul library and the interface defined by ORAN Alliance. The concept is like layer 1 application actually is the function, layer 1 function implement everything through the RE mapping. Then this function, they will call the Fronthaul library. So in OSC, the ORAN software community, they provide the layer 1 application software as a binary code. For Fronthaul library, they provide all the source code. So they have a demonstration. They can use the source code, the binary code, they call the Fronthaul library. The Fronthaul library is used to transmit all the symbol here, the IQ symbol, IQ signal here through the NIC. The NIC is a network interface card. Actually, this is a fiber Ethernet interface card. Here, they will use DPDK. DPDK is a zero copy concept. They want to speed up the transmission between different layers. So they put the data to the memory, so you don't need to copy and it from the software from layer to layer. They can reduce the processing time. For Fronthaul library, the synchronization is quite important because you need to have accurate synchronization at the symbol level. So you need to have an accurate timing source. In Fronthaul library, they use IEEE 15AA as a timing protocol. So this one is for synchronization. In addition to that, the Fronthaul library in Intel's implementation, they can also call FPGA accelerator if you want to do LDPC or protocol encoding decoding. You can use FPGA to speed up the process to reduce the processing time delay. Then we show you what are the open Fronthaul. Open Fronthaul is a lower layer split defined by ORAN Alliance. It's one of the main purpose is to reduce the bandwidth requirement. So that's why they choose the split to RE before the IQ. The Fronthaul library defined by ORAN Alliance. This table actually is come from ORAN Alliance. They have a working group A. They define the Fronthaul library interface. So basically, they are quite simple. They have Fronthaul initialize start. So first of all, this is to initialize all the memory, library model, and the thread. Then they start to process the Fronthaul packet by running the Fronthaul FH start. So here, these four are handler for Fronthaul interface. This is start, stop, close. And since you need to allocate memory for DPDK, so you can use Fronthaul memory to destroy the memory structure. So actually, use this Fronthaul is quite simple. At the beginning, you need to do initialization. Then you can start the Fronthaul, stop the Fronthaul, remove the usage of Fronthaul interface using Fronthaul close. Timing synchronization. Actually, we mentioned the synchronization, so they need to have a grandmaster clock to synchronize to all the ODU need to synchronize with a central clock source, GMC. So they define you can use IEEE 15AA. This is the protocol we just mentioned. You can also use GPS for synchronization. You can use GNSS to get a timing resource. Then it generates one PPS output signal. Then you can use this to sync with the NIC card. This is an example. We show you. You can have first step is you can have a GNSS receiver, so you can generate one PPS. So the ODU will sync up the backup NIC using with the general master clock. Then system clock, actually you also will have other NIC. So this is for clock timing source, but this one is to synchronize among different ODU. So you need to have a clock source using PHC to SYS to synchronize the clock for this ODU. Then the ODU software, they can use this clock as a reference source to get the system clock from the Linux kernel. So Fronthaul library can get the exact time. So when you transmit the packet, you need to carry the timing in Fronthaul library. So Fronthaul library use this process to get all the information. Here, the Fronthaul NIC, they also need to sync up with the system using PTP4L. So this system clock get from a master clock here. The main source for the system clock. This one is for timing generation. In OSC, ORAN Alliance, they define a functional split option 7.2. Implement a function up to resource element mapping in ODU. They can support ORU, implement digital beamforming without pre-coding, or they can implement digital beamforming plus pre-coding. So they call this one category A and the category B. So according to ORAN Alliance, ORU can have two categories. One is easy to implement. Second one is more complicated, but performance is better because you can use pre-coding. You can add a pre-coding function. Here is more complicated to implement. The Fronthaul will transmit IQ sampling sequence of the OFDM symbol in frequency domain for each MIMO spatial string. So this figure is the same as the previous one we show you: scrambling, modulation, mirror mapping, pre-coding, then IE mapping. So after IE mapping, actually you just you will transmit IQ signal. So this is the IQ signal in frequency domain because it's before IFFT. So this is the IQ signal in frequency domain. If you want to transmit, you can further reduce the bandwidth requirement using compression or decompression. So this one, the dashed line is optional. Pre-coding is optional. Digital beamforming is also optional. Then you will do IFFT, you add the CP bank, then you do D2A, then you can do analog beamforming if you like. So we just mentioned you can have option A and B. Category A do not support pre-coding. Category B can allow to support pre-coding. The beamforming video, we just already saw it. Beamforming, actually, they try to adjust the amplitude and the phase of each antenna such that they can reach directional signal transmission and reception. We just mentioned analog and the digital beamforming. Let's quickly go through it. Basically, the major difference is how they want to adjust the weight. So the major difference is whether they adjust weight before or after DA conversion. We use this figure as an example. This is analog beamforming. Analog beamforming is adjust the weight in analog domain. For digital, so actually here, this is the A to D, like the after modulation. This is the multiplier, and this is the modulation. So actually here, they will have A to D. So analog beamforming is they apply the weighting after the A to D. Digital beamforming is they try to adjust the weight before A to D. Here actually is D to A, not A to D. Okay, we consider this figure is for the digital part, for the for the transmitter. All the detail you can refer to this page. They will they show the detail about analog beamforming and digital beamforming. But here, what I want to tell you is what they are doing is they show you the phase. They want to adjust the gain and adjust the delay of the phase. This is what they are doing. If you want to do analog beamforming or digital beamforming, you need to adjust the weight. So it depends on where do you do it. So you can do it in analog domain or digital domain, or you can do hybrid. Means you can do it here plus here. So why do we want to mention this? Because the weighting will be carried later through the open Fronthaul interface. This is the figure for open Fronthaul interface. This is the handset. This is the ORU. This is ODU. This is OCU. Open Fronthaul interface, they define the transmission between the DU and the RU. Open Fronthaul interface, it consists of three parts. The first of them is CU. Second one is synchronization plane. Third one is M plane. So from now on, we start from the lower part of open Fronthaul part. Then tomorrow we will introduce DU and the CU. Then we can introduce the RIC later on Thursday. So the full protocol, M-plane actually is for configuration for network management. It will be related to the ORAN interface we mentioned for ORAN Alliance. S-plane is for synchronization protocol. They use PTP Sync Ethernet, IEEE15AA for synchronization. CU and the DU actually is the IQ signal for control plane and for user plane. So all of them, they will follow the format, the order defined by ORAN Alliance, transmit through the EC-put protocol over Ethernet over fiber. So this is the protocol stack for the three plane. They have CU, S, and the M. CU, the most important part actually is the CU. They transmit the data. Actually, this is a transport protocol. They just use EC-pre over or radio over Ethernet to transmit the IQ signal from C plane and the U plane. S plane, they provide PTP or Sync Ethernet over the Ethernet. PTP is a precision time protocol. M plane is they use wall configuration netcom protocol over SSH over TCP IP. So you can see that configuration, all the configuration information, they will go through SSH. So it ensure the security part. Then the packet will transmit through TCP over IP. So netcom actually is IFC 6241 defined by IETF. This is a general purpose protocol for manage network device. So M-plan is for network management. This video shows the user plan format. Means the user plan format, if you have the chance to check the IP packet, actually this is like IP packet. You will have header, you will have payload. Header show you how the content are organized or processed. Payload carry the real information. Show you first. To remember, we are talking about for EC3, they will carry user plan and the control plan. So this video is for user plan. So let's see what user plan packet are carried. We mentioned they have header and the payload. Header, they consist of majorly 4 information. First one is message type. Second one is payload size. Third one is PCID. PCID is important. It's the source and the destination ID. It's like IP address. You have source address and the destination address. You also have sequence number. Sequence number will define the order for the packet. So this 4 actually is the major information carried in EC3 header here. In ORAN Fronthaul spec, we just mentioned the identifier specify the source and the destination. So how do they define the PCID? The PCID in Fronthaul spec, they have a term. They call it Extended Antenna Carrier, EASC. EASC is used as a message source and the destination identifier. What does it mean? It means that your signal, the packet you want to transmit through the Fronthaul library, the IQ signal, the destination is antenna carrier. We just mentioned you have many antenna. So at the RU side, they need to know which antenna need to transmit this IQ signal. So this is an important term because this is the source and the destination ID. If your ID is wrong, it will transmit through the wrong antenna, so everything will go wrong. What's ESAC? ESAC consists of some information. First one is DU port ID. Second one is band sector. Third one is component carrier ID. Component carrier, what's this? The CC is, we just mentioned, you can have more, you can use carrier aggregation to enhance the data rate. For carrier aggregation, you need to identify the carrier. So the identification is each carrier. They call it a component carrier. So you need to determine a component carrier. Then you can know the symbol will be transmitted in which component carrier. RU port ID is RU port ID you want to transmit. So ESAC define which DU transmit to which RU. So this is the, as we mentioned, the Fronthaul protocol is one DU can control many RU. So you can use the ESAC to know the DU and the RU. For the payload part, actually, they can be simply divided into 5 parts. For the payload part, they have control information. They have data. Data is the IQ signal you want to transmit, either compressed or not compressed. So here you can find that the data, they show you the first RE in the PRB, the first RE in PRB, then will show you many sample for different RE in the PRB. So means that they transmit one resource element one by one, symbol by symbol. Each RE is equal to 12 subcarrier multiplied by one symbol. Actually, this is the unit of RE. So they transmit each symbol in sequence. But how do you carry the information, characterize the information for the RU? Because the RE is determined in terms of time and the frequency. So you need to use the time and the frequency information to determine the location, the position of the RE. For time resource information, they will specify frame, subframe, slot, and OFDM symbol. Okay, so you can use time resource information to know this is the OFDM symbol for which slot in which subframe during which frame. For frequency resource information, they will show you the start position of the OFDM symbol. They show you the starting time and the number of PRB you are used. So for each part, they will show you this show you the time information, this show you the frequency information, where is the starting frequency and how many subcarrier do they carry. Then this is the IP compression information. All this part is related to the data. So the first part is how do you compress the IQ signal. Then the rest of the part is IQ sample sequence of the OFDM signal. I told you the frame format for the youth plan is common in both direction, means from ODU to ORU and the ORU to ODU. So for this part, so the first byte, you can see the distance is the length is 8 bits, is 1 byte. So the first one show you how do you do your compression. Offline is your IQ sample. So this is for U plane. Then this is for C plane. Actually, the concept for C plane is almost the same as U plane. You have header, you have time, information, IQ compression information, then resource information. So format is same as uplane. So header and the payload. Payload here. So we just mentioned the IQ signal is transmitted in the uplane. So what does C plane? What's the purpose for C plane? Because the timing of the IQ signal, the time frequency for the time and frequency for the symbol of the IQ signal already be carried in U plane. So C plane show you when do you want to transmit. And the most important for the EC payload is they want to specify the beamforming weight for IQ signal. So this is the weight we just mentioned before. So the weight, they will, what are the weights? They will show you the time resource information, IQ compression, control information, and frequency resource information, star PRB, and the number of PRB, and the bin identifier, which bin are you talking about? So the beamforming weight will be related to the bin. So for this one, they show you. So they show you the time information, IQ compression information, the frequency resource related information. The last part is a bin identifier. For control plane, for ODU, the delay management is quite important. They need to know the round trip delay, so they use a transmit window to adjust it. So the concept is, if you want to transmit a symbol at this time moment, you need to add some time for the ORU processing. Then you need to advance the transmission time by a window. So such that ODU need to transmit in advance. So actually this is an extra time delay introduced due to the Fronthaul interface. If you don't have Fronthaul interface, ODU process, they can direct transmit the symbol. So you are not start to process the symbol here, but you still need to consider the processing delay for ODU. So you need to start to process the symbol 0 here, then you are able to transmit here. So this is the total processing delay for the transmitter. S-plane is used for synchronization. M-plane, they have two architecture. They have a hierarchical and or hybrid architecture. The major difference is here you can see the NMS. Actually, this is network management system, subsystem. Actually, this is the ORAN interface. The SMO, we will talk on Thursday. So for this one, they define for hybrid mode, you can use ORAN network interface, NMS to configure ODU, then use ODU to configure ORU, or they can also have another pace. They can have a dedicated management pace to configure ORU. But for hierarchical module, actually they still have MAS. The MAS will communicate with ODU, then ODU will configure ORU directly. So here is a function. Basically, is startup, software management, configuration management, performance management, form management. So these are the basic management function provided by the ORAN Alliance. So they have some. Okay, so this is software management. Why do they need to do it? Because we have mentioned the ORU and the ODU. They can be managed. They can be implemented by different vendors. So when ODU want to manage ORU, ODU may have their control information. They may have their software. They may use to upgrade, update the ORU. So they can use this software management procedure to, first of all, get the ORU software information. Then they can get all information. If they need to maintain it, they can download the new software to ORU. They can then install it to ORU. They can then activation the new software to ORU. So if you, it's actually, this is quite simple to your handset you are using today. To buy a handset, you need to check, always check the network, will always check your server, will always check your version. If they have a new version, they will ask you to download it, install it, activate it again. So here are some information. Okay. Here are some detail for this part. I guess we don't have too much time. Here I just summarize all the information defined in the spec, so you can check the spec for detail. The last page I want to show you to conclude the Fronthaul is the Fronthaul topology. In ORAN Alliance, they define two Fronthaul topology. First one is point-to-point. Second one is layer 2 switch. For the first one, you can have ODU. One ODU, you can serve multiple, you can control multiple ORU. But each of them, they need to have a dedicated fiber between ODU and ORU. This also means for the ODU, you need to have multiple network interface card, such that you can control them individually. So this is point-to-point. It's quite simple. The major cost is you need to have a fiber for each ORU. For the second approach, they call it layer 2 switch approach. Means that maybe you can use a trunk. You can use the Ethernet connect. We have mentioned the ODU. You can put ODU in the cloud or to the edge. If you put ODU at the edge, maybe the distance between ODU and ORU is not far away, so they can have a direct fiber connection. But ODU, as we mentioned, you can also put it to the cloud. If you want to put it to the cloud, it will not be efficient to use individual fiber to connect to each of the RU. So you can use a high-speed fiber, connect to a layer 2 switch, then use the layer 2 switch to bridge it to different RU. So the case 3 actually is a simplified case for point-to-point. The main benefit is you can save the total cost of the the fiber. In the first one is they can also connect. You can also consider to have low speed fiber to layer 2 switch. Then you can use a trunk to interconnect two layer 2 switch. So compared to this one, you need to have a very high speed trunk from here to here. But maybe the cost is too high. So maybe you can consider to use two layer 2 switch. The major difference here is here you only need to have 25 gigabit per second NICA in ODU. But in here, if you want to use the trunk, it would be 100 gigabit BPS trunk. So the NICA here would be different. So here you can use a low cost NICA. Then you can use two layer 2 switch interconnect by the fiber. The middle one, the case 2, is they can consider whenever, for example, this RU, they can provide a pass switch if some pass is failed. So you can have two RU. This RU may be a backup RU. This is a mandatory RU. So if there's a pass failure, they can automatic switch to another pass. So it's a concept. Actually, maybe you can have two fiber to the same RU, so they can automatic switch the pass. So, okay, here is the conclusion of our talk today. If you have any question.
Okay, thank you, Prof. Ray, for your lecture. Please, if any question, you can ask to Prof. Ray or just write in chat box.
So let's see whether we have one question mentioned before. I already mentioned, answer it. So do you find any question? So today, I just go through the Fronthaul. Fronthaul is a RU, between RU and the DU. So from tomorrow, I will try to go through more detail about the DU and the CU part. So if you don't have questions, so maybe we can.
Okay, Prof, before we close this meeting, maybe we take
a photo, okay?
Okay, Pak Infal, can you help us to take a picture? Okay, we'll take picture for the first page. We'll count 1, 2, 3. Okay, next page. Okay, please, next page. Wait a moment. 1, 2, 3. It's okay. Thank you.
Thank you.
Thank you, Prof. Ray. Thank you.
Thank you very much, everyone.
See you tomorrow.
For the lecture. See you tomorrow.
Okay, see you
you tomorrow.
tomorrow, everyone.
Bye.
Bye.
Bye.